So hello learner, once again I welcome on the class of hydraulic engineering. So I hope you all are safe and good health. So in the previous discussion we have seen about the boundary layer theory. So in the boundary layer theory I have discussed about the concept of boundary layer, and after that what is boundary layer thickness. So about the boundary layer thickness I told you the definition that it is the thickness it is the thickness where our local velocity is approximately 99% of the free stream velocity. And after that I told you that this boundary layer thickness is the approximate value. So there are three mathematical expression were derived. The first one is displacement thickness, second one is momentum thickness, and after that third one is energy thickness. The expression of displacement thickness I have derived, that is integration of 0 to delta 1 minus small u by capital U into dy, where small u is the velocity at a distance y from the leading edge, and after that capital U is the free stream velocity. And similarly I have derived the momentum thickness. So the expression of momentum thickness is integral of 0 to delta u by capital U into 1 minus u by capital U into dy. And the last one I have derived the energy thickness, that is integral of 0 to delta u by u into 1 minus small u square by capital U square into dy. And after that I have discussed the shape factor, and shape factor is defined as the ratio of displacement thickness to the momentum thickness. And after that I have compared these three mathematical expression. So we have concluded that the displacement thickness is higher magnitude, and after that energy thickness, and the least value is momentum thickness. So today I will discuss about the boundary layer along a long thin plate and its characteristics, and after that I will discuss the what is laminar sublayer and boundary condition for this region, and after that I will discuss the velocity profile for the laminar and turbulent layer. And once, if we don't know the value of velocity profile, then how will we compute the value of drag coefficient, local drag, average drag? That will be I will discuss, and this concept was given by Blasius. So I am taking one question, and the question is the velocity distribution within this boundary layer is given by u by capital U is equal to y by delta to the power 1 by n. Obtain the ratio of displacement thickness to the momentum thickness. So the solution of this, the velocity distribution is given capital U by small u by capital U, that is y by delta to the power 1 by n. So we have to compute the ratio of displacement thickness to momentum thickness. So displacement thickness delta star is equal to 0 to delta 1 minus u by capital U into dy. So we can write 0 to delta 1 minus velocity distribution is given, so y by delta to the power 1 by n dy. So if I integrate this value, so we can write delta star is equal to 0 to delta dy minus 0 to delta y by delta to the power 1 by n into dy. So the integral of dy is y running from 0 to delta minus, if I take out delta to the power 1 by n out, so it is y to the power 1 by n dy. So the integration of 1 by n plus 1 divided by 1 by n plus 1 running from 0 to delta. So we can write delta minus 1 by delta to the power n into this value is n by n plus 1 into delta to the power 1 by n plus 1. So we can write delta minus this value is n by n plus 1 into, we can write delta to the power 1 by n into delta. So delta to the power 1 by n cancel, so it is delta. So n delta plus delta minus L delta divided by n plus 1. So the value is delta by n plus 1. So the displacement thickness is delta by n plus 1. Similarly, we can compute the momentum thickness. So momentum thickness is theta is equal to expression of momentum thickness 0 to delta u by capital U into 1 minus u by capital U into dy. So we can write 0 to delta, and the velocity distribution is y by delta to the power 1 by n into 1 minus y by delta to the power 1 by n into dy. So we can write 0 to delta y by delta to the power 1 by n into dy minus 0 to delta y by delta to the power 2 by n into dy. So if I integrate the value, so this is delta to the power 1 by n, y to the power 1 by n plus 1 running from 0 to delta. If I integrate, so this is also 1 by n plus 1 minus 1 by delta to the power 2 by n, y to the power 2 by n plus 1 divided by 2 by n plus 1 and integral 0 to delta. So if I write, so this value is n by n plus 1 into 1 by delta to the power 1 by n into delta to the power 1 by n plus 1 minus n by n plus 2 into 1 by delta to the power 2 by n into delta to the power 2 by n plus 1. I hope you are understanding. 1 by delta to the power n, integral of y to the power 1 by n is 1 y to the power 1 by n plus 1 and divided by 1 by n plus 1 running from 0 to delta. Similarly, 1 by delta to the power 2 by n is constant, so I have taken out. So it is 0 to delta y to the power 2 by n into dy. So the integral of y to the power 2 by n is y to the power 2 by n plus 1 divided by 2 by n plus 1 running from 0 to delta. Now I have put the value. So this value is 1 by n plus 1. So n by n plus 1 into 1 by delta to the power n, and I have put the value of delta in place of y. So it is delta to the power 1 by n plus 1. Similarly, this value is 2 by n plus 1, so n will go up, so n by n plus 2 into 1 by delta to the power 2 by n into delta to the power 2 by n plus 1. So we can write theta is equal to, if I take, so 1 by delta to the power n by 1 by n, and we can write this is delta to the power 1 by n into delta. So delta to the power 1 by n and delta to the power 1 by n cancel. So this value is n delta by n plus 1. Similarly here we can write delta power 2 by n into 1. We know x to the power m into x to the power n is x to the power m plus n. So with the concept of that, we can write delta to the power 2 by n into delta. Delta cancel out. So we can write n delta divided by n plus 1 minus this value is n delta by n plus 2. So if I write n delta by n plus 2, so the n plus 1 into n plus 2, so this value is if I take n delta is common, so n plus 2 minus n minus 1. So it is coming n delta, n cancel, divided by n plus 1 into n plus 2. So momentum thickness is n delta divided by n plus 1 into n plus 2. So we have to uh, compute the ratio of displacement thickness to momentum thickness. So we can write delta star divided by theta. So displacement thickness is how much? Delta by n plus 1. So we can write delta by n plus 1 divided by n delta by n plus 1 into n plus 2. So we can write delta by n plus 1 into n plus 1 into n plus 2 divided by n delta. So n plus 1 n plus 1 cancel, delta delta cancel. So it is coming n plus 2 by n is the momentum thickness. Similarly, if I take another problem, so the velocity distribution, the velocity distribution of a boundary layer is given by u by capital U is equal to 3 by, sorry, so it is 3 y by delta minus 2 y by delta whole square. The ratio of displacement thickness to boundary layer thickness. So the same problem, that is the solution. The velocity profile is given, u by capital U is equal to 3 y by delta minus 2 y by delta whole square. So the displacement thickness is equal to 0 to delta 1 minus u by capital U into dy. So if I put, so displacement thickness is equal to 0 to delta 1 minus 3 by 2 y by delta and plus 2 into y by delta whole square dy. So the delta star is equal to 0 to delta dy minus 3 by 2 0 to delta y by delta into dy plus 2 0 to delta y by delta whole square into dy. So it is delta minus 3 by 2 delta into y square by 2 running from 0 to delta plus 2 by delta square, it is yq by 3 running from 0 to delta. So it is coming 3 by 2 minus 3 by 4 delta square by delta means delta plus 2 by 3, this is delta cube by delta square, so delta. So if I put, so 3 delta plus 2 delta, 5 delta by 3 minus 3 by 4 delta, 3 delta plus 2 delta, 5 delta by 3 minus 3 by 4 delta, so it is 12, 20 delta minus 15 delta. So it is coming 5 delta by 12. So we have to take the ratio of displacement thickness to the boundary layer thickness. So the displacement thickness is 5 by 12 delta. So if I take 5 by 12 delta by delta, so it is coming 5 by 12. So second problem I have solved. Now I am going to start boundary layer along a long thin plate and its characteristics. So we have to see the boundary layer along a long thin plate along and its characteristics. So let us assume this is our plate. This is our thin plate. This zone, this point is called leading edge. This region is called laminar region. This region is called transition. And this region is called turbulent region. So what is laminar region? What is transition region? What is turbulent region? I will discuss one by one. So if I discuss about the velocity distribution, so this was our thin plate. This region so as I told you, if I draw the velocity distribution, this is y. This point I told you that this is the leading edge. This region is laminar region. So if I draw the velocity distribution, this is delta. Similarly, if I draw the velocity distribution, and if I draw the once again the velocity distribution, so the velocity distribution in laminar region, this region is laminar, this region is transition, and this region is turbulent. So the distribution of velocity is in laminar region is parabolic, and in turbulent region it is logarithmic. So the velocity distribution in the turbulent region is logarithmic, and the velocity distribution in laminar region is turbulent. So we can write in laminar region the velocity distribution is parabolic. So we can write capital U by y, small u by capital U is equal to y by delta whole square. So this is the velocity profile in laminar region. Velocity profile in laminar region. Here u is the velocity at a distance y from the leading edge. Capital U is the free stream velocity. Delta is the boundary layer thickness. So this is the velocity profile we have seen. Similarly, if I discuss the velocity profile, so in turbulent region, the velocity profile, the velocity distribution is logarithmic, and the velocity distribution follows velocity distribution follows 1 by 7th power law. Means if I write the velocity distribution, so it is y by delta to the power 1 by 7. So with the help of this velocity distribution, we can identify which type of flow is there. If the velocity distribution is given parabolic, means there is a laminar flow, and if the velocity distribution is either logarithmic or follow 1 by 7th power law, means our flow is turbulent. So what is the boundary condition in this region? So the next heading is boundary condition. So boundary condition, we can see the first boundary condition we can write at y is equal to 0, means at leading edge at y is equal to 0, our boundary layer thickness is equal to 0. So this is the first boundary condition. At y is equal to 0, our boundary layer thickness is 0. Sorry, at x is equal to 0, not y. At x is equal to 0, our boundary layer thickness is 0. Similarly, we can write second boundary condition. At y is equal to 0, our local velocity is 0. We can see here, this is x. So at x is equal to 0, boundary layer thickness is 0. At y is equal to 0, we can see at y is equal to 0, our velocity is 0. So second boundary condition, at y is equal to 0, our local velocity is 0. Third condition, we can write at y is equal to delta, our velocity is free stream velocity. Free stream velocity means this is the definition of boundary layer thickness. At a distance of delta, u is approximately 99% of u, means approximately equal when our y is equal to the boundary layer thickness. And the fourth condition, at y is equal to delta, del u by del y is equal to 0. And the fifth condition, at y is equal to delta del 2 u by del y square is equal to 0. So these are the 5 boundary conditions that is very important in the boundary layer. The first one is at x is equal to 0, means at leading edge our boundary layer thickness is equal to 0. Second condition, that is at y is equal to 0 our local velocity is equal to 0, and when at y is equal to delta our local velocity is converted in the free stream velocity, and at y is equal to 0, so del u by del y, because u after y is equal to delta the velocity is constant, that's why del u by del y is equal to 0, and at y is equal to delta del 2 u by del y square is equal to 0, because this is the constant velocity. So these are the 5 boundary conditions we have to remember. So if I write all the 5 boundary condition, so boundary condition, that is very important. Once again I am telling this boundary condition. So this is our thin plate, long thin plate. If I draw, so this is the turbulent region, this is y and this is x, this is the leading edge. So we can first boundary condition I have written at x is equal to 0, delta is equal to 0. Second boundary condition, at y is equal to 0 our local velocity is equal to 0. Third boundary condition I have written at y is equal to delta local velocity is equal to the free stream velocity, at y is equal to delta del u by del y is equal to 0, and the last boundary condition I have discussed, that is at y is equal to delta del 2 u by del y square is equal to 0. So this boundary condition we have to remember. So dear student, today I have discussed about the some problems related to the displacement thickness, momentum thickness and energy thickness. In the first problem, the velocity profile is given, that is u by small u by capital U is equal to y by delta to the power 1 by n, and we have to compute the ratio of displacement thickness to the momentum thickness. So displacement expression of displacement thickness is integral of 0 to delta 1 minus small u by capital U into dy, and the expression of momentum thickness, that is theta is equal to integral of 0 to delta u by u into 1 minus u by u into dy. So with the help of that we have computed the displacement thickness and momentum thickness, and we have computed the ratio of displacement thickness to the momentum thickness. It is simply the integration. In the second problem, the velocity profile is given, and the given velocity profile is u by capital U is equal to 3 y by delta minus 2 y by delta whole square. So in this problem we have to compute the ratio of displacement thickness to the boundary layer thickness, that is delta star by delta. Firstly we should understand the problem. So if this velocity profile is given and the 4 option is given, which type of flow profile is possible, laminar, turbulent, transition, or none of these? So definitely the flow will be laminar, because I told you that for the laminar flow the velocity distribution is parabolic, and for the turbulent flow the velocity distribution is logarithmic and follow 1 by 7 power law. So in this problem same thing we have computed, displacement thickness and delta star by delta we have computed. And after that I have discussed the boundary layer along a long thin plate and its characteristics. So boundary layer along long thin plate, we have drawn the velocity distribution and discussed that in laminar flow our velocity distribution will be parabolic, and in turbulent flow our velocity distribution will be logarithmic, and the velocity profile for the laminar is u by small u by capital U is equal to y by delta to the power 2, and for the turbulent flow u by capital U is equal to y by delta to the power 1 by 7. And after that, I have discussed about the boundary condition used in the boundary layer. So this boundary condition, I have 5 boundary condition I have discussed. When our x is equal to 0, our boundary layer thickness is equal to 0, means at leading edge our boundary layer thickness is 0. Second boundary condition, at y is equal to 0, the local velocity or small u is equal to 0. Third boundary condition I have discussed, at y is equal to delta, means at when y is equal to the boundary layer thickness, our local velocity is equal to the free stream velocity. And the fourth boundary condition, that is at y is equal to delta, derivative of local velocity with respect to y is equal to 0, because when at y is equal to delta, our local velocity is equal to capital U, and after that this velocity will be constant, so the derivative will be definitely 0. And the fifth boundary condition I have discussed, that is at y is equal to delta, second derivative of this local velocity will also 0. So these 5 boundary condition we have discussed today. So in the next class, I will discuss what is laminar sublayer, what is the expression of laminar sublayer thickness, and after that I will discuss the Blasius equation. In Blasius equation, I will discuss different expression like what is the expression of delta by x, what is the expression of drag coefficient, what is the expression of frictional drag, and what is the expression of drag force for one side of plate or both side of plate. And after that I will discuss the turbulent boundary layer, and in turbulent boundary layer same expression I will discuss, different parameters I will discuss, and after that I will discuss the boundary layer separation. So take care of your health and happy learning.